into detail about metamorphic petrology, I would like to emphasize its significance to civil engineering. For millions of years, metamorphic rocks have been existing on Earth. They come in range of forms, sizes, and colors. Relating it to civil engineering, metamorphic rocks can be used to build structures. For instance, marble can be used in sculpture and as a decorative material. In addition, quartzite is a very hard rock which is usually crushed and used in railroad track construction. Slate and schist are also common building and landscaping materials. With that being said, understanding metamorphic petrology is extremely important to civil engineering.
So let's talk about metamorphic petrology. In order to understand metamorphic petrology, we need to define first what is metamorphism. So the word metamorphism comes from the Greek meta, meaning after, morph, meaning form. Therefore, metamorphism means the after form. In geology, this refers to the changes in mineral assemblage and texture that result from subjecting a rock to pressures and temperatures different from those under which the rock originally formed. So, the original rock that has undergone metamorphism is called the protolith. It is also known as parent rock. Protolith can be any type of rock, and sometimes the changes in texture and mineralogy are so dramatic that it is difficult to distinguish what the protolith was. Metamorphism occurs at temperatures and pressures higher than 200 degrees Celsius and 300 megapascals. With that being said, rocks can be subjected to these higher temperatures and pressures as they become buried deeper in the earth. Such burial usually takes place as a result of tectonic processes such as continental collisions or subduction. Moreover, the upper limit of metamorphism occurs at the pressure and temperature of wet partial melting of the rock in question. Once melting begins, the process changes to an igneous process rather than a metamorphic process. So there are 5 main factors that control metamorphism. The first one is the mineral composition of the parent rock. The parent rock, also known as the protolith, is the rock that forms prior to metamorphism. Either of the 3 rock forms, sedimentary, igneous, or metamorphic, may be used. The critical feature of the parent rock is its mineral composition. This is because the stability of minerals, or simply how they were influenced by changing conditions, and it is what matters when metamorphism takes place. To put it in another way, when a rock is exposed to higher temperatures and pressures, certain minerals undergo chemical reactions and transform into new minerals, while others can simply change shape. The next one is the temperature at which metamorphism takes place. Temperature is a key variable in metamorphism. High temperatures occur near to igneous intrusions, where the magma hits the surrounding rocks. Temperature also increases with depth, due to the geothermal gradient. Therefore, as temperature increases, the rate of metamorphic reactions also increases. This is because many of the chemical reactions require heat to take place. Higher temperatures increase the rate at which ions diffuse between minerals, though it is still a slow process because the ions have to move through solid rock during metamorphism. The whole process is greatly speeded up by water. The main reason for that will be discussed in the 4th factor that control metamorphism. So for the 3rd factor that control metamorphism, which is the amount and type or direction of pressure during metamorphism, pressure is important in metamorphic processes for 2 main reasons. First, it has implications for mineral stability. Second, it has implications for the texture of metamorphic rocks. In the figure below, rocks that are subjected to very high confining pressures are typically denser than others because the mineral grains are squeezed together as shown in figure A, which is the equal confining pressure where the pressure is essentially equal in all directions. And because they may contain mineral polymorphs in which the atoms are more closely packed because of plate tectonics, pressures within the crust are typically not applied equally in all directions. In areas of plate convergence, the pressure in one direction perpendicular to the direction of convergence, is typically greater than in the other directions, as what shows in the figure B, which is the directed pressure, where the pressure from the sides is greater than that from the top and bottom. In situations where the different blocks of the crust are being pushed in different directions, the rocks will be subjected to shear stress, and it is shown in the figure C, which is the shear stress caused by different blocks of rock being pushed in different directions. For the fourth factor that controls metamorphism, which is the amount and type of fluid, mostly water, that is present during metamorphism, water is the main fluid present within rocks of the crust. The presence of water is important for two main reasons. First, water facilitates the transfer of ions between minerals and within minerals, and therefore increases the rates at which metamorphic reactions take place. With that being said, while the water doesn't necessarily change the outcome of a metamorphic process, it speeds the process up, so metamorphism might take place over a shorter time period, or metamorphic processes that might not otherwise have had time to be completed are completed. Secondly, water, especially hot water, can have elevated concentrations of dissolved substances, and therefore it is an important medium for moving certain elements around within the crust. Therefore, not only does water facilitate metamorphic reactions on a grain-to-grain basis, it also allows for the transportations of ions from one place to another. For the last or fifth factor that control metamorphism, the amount of time available for metamorphism, most metamorphic reactions take place at very slow rates. For example, the growth of new minerals within a rock during metamorphism has been estimated to be about 1 mm per million years. For this reason, it is very difficult to study metamorphic processes in a lab. Furthermore, while the rate of metamorphism is slow, the tectonic processes that lead to metamorphism are also very low. So in most cases, the chance for metamorphic reactions to be completed is high. For example, one important metamorphic setting is many kilometers deep within the roots of mountain ranges. A mountain range takes tens of millions of years to form, and tens of millions of years more to be eroded to the extent that we can see the rocks that were metamorphosed deep beneath it. So, there are two main types of metamorphic rocks. The first one is foliated metamorphic rocks, which are formed in an environment with either directed pressure or shear stress. Here are some of the examples of foliated metamorphic rocks: slate, pyrite, gneiss, schist, granulite, and migmatites, which are mostly formed during convergent plate boundary since it produces a lot of direct pressure and shear stress. The second one is non-foliated metamorphic rocks. They are formed in an environment without directed pressure or relatively near the surface with very little pressure at all. Here are the examples of non-foliated metamorphic rocks: amphibolite, hornfels, quartzite, and marble, which are mostly formed around igneous intrusions where the temperatures are high but the pressures are relatively low and equal in all directions. So, for the next topic, the metamorphism in relation to plate tectonics, metamorphic rocks are result from the forces active during plate tectonic processes. These are the collision of plates, subduction, and the sliding of plates along transform faults create differential stress, friction, shearing, compressive stress, folding, faulting, and increased heat flow. The tectonic forces deform and break the rock, creating openings, cracks, faults, breccias, and zones of weakness along which magmas can rise. So, generally speaking, the greater the tectonic forces, the higher the pressures and temperatures affecting a rock mass, and the greater the amount of resulting structural deformation and metamorphism. So for divergent plate boundary in relation to metamorphism, divergent boundaries are characterized by a rift in the surface of the Earth along the mid-ocean ridges. The ridges are composed of volcanic mountains that erupt basalt onto the surface of the ocean and by that process create new oceanic crust. In this plate margin, chemical action of fluids is the major agent of change causing metamorphism. Seawater circulates through the cracks in the hot volcanic rocks and heated up to 400 degrees Celsius to 450 degrees Celsius. This hydrothermal water attempts to equilibrate with the crust and reacts with unstable olivine, pyroxene, and plagioclase to form new minerals. These new minerals are epidote, sodium-rich plagioclase, and serpentine, typical of green schist facies metamorphism. Then the metamorphic rock is called metabasalt. So for the convergent plate boundary in relation to metamorphism, convergent plate boundaries are located where lithospheric plates are moving towards one another. Most metamorphic rocks in the continents were created at convergent plate boundaries. In the deeper roots of this magmatic belt, foliated metamorphic slates, schists, and gneisses are produced, while in the deeper parts of a mountain belt, metamorphism can become intense enough to produce migmatites. For transform plate boundary in relation to metamorphism, transform plate boundary is located where plates slide sideways past each other. The most characteristic type of metamorphism that occurs at transform plate boundaries is caused by the horizontal shearing motion. As the two plates grind against one another, fault breccias and fine-grained myelonites are created. So, there are three main types of metamorphism. The first one is contact metamorphism, the second is the dynamic metamorphism, and the last or the third one is the regional metamorphism. So, in contact metamorphism, metamorphic rocks that form under either low pressure conditions or just confining pressure do not become foliated. In most cases, this is because they are not buried deeply, and that the heat for the metamorphism comes from a body of magma that has moved into the upper part of the crust. Contact metamorphism is the name given to the changes that take place when magma is injected in the surrounding solid rock or country rock. With that being said, heat is the primary factor of the formation of metamorphic rocks in contact metamorphism. For dynamic metamorphism, it occurs along fault zones where rocks have been altered by high differential pressure. Rocks formed by dynamic metamorphism are restricted to narrow zones adjacent to faults and are known as myelonites. Myelonites are commonly hard, dense, fine-grained, and contain thin laminations. For that reason, pressure is the primary factor of the formation of metamorphic rocks in dynamic metamorphism. For the regional metamorphism, it includes any metamorphic process that occurs over a large region. It is therefore the most widespread and common type of metamorphism. Rock can be metamorphosed simply by being at great depths below the Earth's surface, subjected to high temperature and the great pressure caused by the immense weight of the rock layers above. Much of the lower continental crust is metamorphic. Therefore, heat and pressure are the primary factors of the formation of metamorphic rocks in regional metamorphism. And that's all for metamorphic petrology. So generally, it's really important for us to understand it as it gives us knowledge about how the metamorphic rocks are formed in different processes. Thank you for listening.